Okay, welcome everyone. My name is Andrey Chubukov. I'm from University of Minnesota. So I'll start this enterprise, and because I'm the first, part of the talk will be hopefully not that boring, but maybe somewhat boring, because I want to really start with theory of superconductivity. So you'll hear stuff that you all know, but I will try to put it from a slightly different angle, something that is not always in textbooks. So let's start. Let me ask first the question. I will ask several questions of the audience, and you ask me questions. Let's play this game. You try to interrupt me every time you want. If I don't finish right now in the first talk, I have a second talk to give today. So I can always continue. Rafael, I have a question. Yeah, good. So really, interrupt me and ask questions. Superconductivity. I was going to ask how much everyone knows about superconductivity, but I'm sure you know everything. So zero resistance state of interacting electrons. If you take non-superconducting metals, its resistance is finite at 0 temperature. If you take a superconductor at particular temperature, it drops to 0. Phenomena started in 1911 by this wonderful story about Kamerlingh Olus and his colleague who slept at the proper place at the proper time and didn't change apparatus. So this is how they measure this stuff in mercury. What we need for superconductivity. This is important to start with. You have a conventional metal. Then we know what happens in the conventional metal, Drude theory. Drude theory tells you that you apply electric field, you get current. Current is proportional to the field. Simple story is that electrons are flying before they hit another electrons, then they change direction, and this is how you get resistivity, matter, which is inversely proportional to conductivity. Conductivity is a proportionality coefficient between current and the field, and everything is fine here. There is no infinity, no zeros, and this is, by the way, dissipative current. In order to sustain current, you need to constantly borrow energy from the source of electric field. So this is a conventional theory. Everything is finite. However, it has been known even before theory of superconductivity has been developed and superconductivity has been understood, that if somehow the system has a macroscopic wave function, described single wave function, described by amplitude and a phase, global phase, then by quantum mechanics rules, you take this wave function, you write an expression for the current, quantum mechanical expression for the current, and you find that there is extra current proportional to this phase of this macroscopic condensate, macroscopic wave function of 10 to 23 systems in the same quantum mechanical state. And this is not accompanied by energy dissipation. And as a result, this current would exist even if your electric field is 0. And the presence of a current, finite current, when the electric field is 0 means that this coefficient is infinite, or inverse of this coefficient is 0. This exactly means that resistance is 0. So you need a macroscopic wave function. You need a macroscopic condensate. And then the story goes on. First of all, this condensate breaks U1 symmetry. There is a phase. So you need to have a global phase. You don't know what its value is. So system spontaneously breaks U1 symmetry. And there is a wonderful mechanism which goes by the name of Anderson in condensed matter community, by the name of Higgs in high energy community. Basically, it's like this. Vector potential eats up fluctuations of this phase, becomes massive. And because vector potential becomes massive, this basically means that magnetic field is expelled from the superconductor. And this is nothing but Meissner effect. And this is the source of infinite number of demonstrations with superconductors. You can put sumo wrestler on a superconductor, you see the gap, or you can put aquarium with the golden fish, and aquarium will be levitate on top of superconductors. So levitation experiments is, when I saw it first time when I was younger than you guys are now, then I was really amazed. Okay, so in a simple version of the story, once we have macroscopic condensate, we have superconductivity. Great. The question is, what we need, how condensate appears. For bosons, this is obvious. Condensate should appear. It's called Bose-Einstein condensation. Bosons tends to accumulate at a state with zero momentum, and, and this, of course, macroscopic state with this macroscopic wave function. But obvious statements. Electrons are not bosons. Electrons are fermions, and two fermions cannot simply be in the same quantum mechanical state. Great. Next, also something that you all know very well. If somehow two fermions form a bound state and becomes bosons, the rest of the story is look at the story for bosons. The bosons will eventually condense. Great. So this all means that all we need is to find a way for fermions to form bound state, right? This is the story about superfluidity and the story about superconductivity, how to form superfluidity of helium-3, and how to pair fermions into bound state. But for this, we need attraction between fermions, right? And by the way, it's not guaranteed. If you are just looking at a quantum mechanical problem whether small attraction gives you bound state, the answer is not necessary, right? If you are in 3 dimensions, it's not guaranteed to you. So there are 2 issues, and let me address both of them. The talk is called Eliashberg theory of superconductivity. It will appear in about 15-20 minutes, because I need to tell you what was before Eliashberg theory of superconductivity, what is built upon. And then we discussed about different versions of Eliashberg theory. Some of them are not in any way affiliated with the name of Eliashberg, but just called this way. Some affiliated with the name of Eliashberg. So, how to get attraction? That's number 1 question. Number 2 question, how strong attraction should be for superconductivity? Second question is easier to answer. So let me start with something that is easier to answer. And for this, there is a story that some people may know better than me about how Bardeen-Cooper-Schrieffer eventually came to theory of superconductivity. And the story was that there was a young scientist by the name Leon Cooper who was giving talks in various places, telling that if 2 fermions attract each other, no matter how small attraction is, you always form bound state. Apparently, from what I was told, nobody could understand why the hell this happens, except Bardeen. Bardeen understood. And this is how Cooper started working with Bardeen, and then eventually how theory of superconductivity came in. But the story from Leon Cooper was that already arbitrary small attraction between fermions is capable to produce you bound state in any dimension. And the argument, simple argument here is that for fermions in condensed matter physics are not fermions in high energy physics. In some sense, even if you have dispersion k squared over 2m, you don't have to count powers of k when you do calculations, because the 0 energy state is not state with k equal to 0, but a state with finite k. You have a chemical potential in the system. And therefore, locus of 0 energy point is a surface with finite kf. Therefore, take any d-dimensional integral over k. The actual interesting variation is k minus kf. So you are always spatially in 1 dimension in this regard. At time, give you 1 plus 1, and in 1 plus 1, you have bound state. What I want to do, I want to look at this argument from Fermi-liquid perspective and ask question, which obviously certain to produce an answer, but let's see how it produces an answer. And question is like this. Yes, we know that there is some logarithmical singularity coming from the fact that if you calculate pairing susceptibility, because of the presence of the Fermi surface, you will see there are some logarithms in the theory. What it means? There are a number of issues when you have logarithms in the theory and nothing happens. Moreover, the theory flows to, in fact, 0 coupling. Sometimes it's called Moscow 0 many years ago, because it was a flow of RG flow of the coupling constants that instead of diverging goes to 0. For singularity, for instability, you need something different. So it's not guaranteed in some sense that if you have some logarithmical singularities in the theory, then it will produce you something. So starting from this slide, from next slide, you will see I will put some handwriting. And if you cannot read my handwriting, I will do it for you. So I'll be reading essentially what I put in. So let's start with the Fermi-liquid theory. And let's try to ask a question. Yes, we know that there are some logarithms. What it means? And let's try to follow the rules. And rule number 1 is that we want to understand bosonic excitations in a fermionic system. Open textbooks, and textbooks will tell you, yeah, we know how to do it. You need to calculate vortex function, which is fully dressed, anti-symmetrized interaction, anti-symmetrized because fermions, if you exchange two fermions, you change sign, that's all you do. And poles of this, sometimes two-particle green functions are cubically called vortex functions, tell you what are bosonic excitations in the system. And why it's important for us? Because for stability of the system, these bosonic excitations viewed in a complex plane of frequency, excitations are frequency is equal to something. So this frequency at which bosonic excitations exist, in which this function, vortex function, has a pole, there must be in the lower half plane. What it means physically? It means that if you shift system a little bit, create some perturbation to the system, this perturbation will die off exponentially with time. If somehow pole will go from lower to upper half plane, this means that any perturbation will grow exponentially with time, not decay. And this would mean instability. So let's check what happens when we take a system of fermions, allow interactions, and then see what's going on. So one example, zero sound pole. Zero sound is some part of curriculum of all classes of condensed matter physics. And there are poles at frequency equal to momentum times velocity, which is close but not exactly equal to Fermi velocity. But we need to go a little bit further than this and ask, where is this pole, in which half plane? You always have minus I delta. So pole is very close to real axis, zero sound pole, but always slightly below real axis, which means that zero sound excitations, if you excite zero sound as the system, it will decay. It will die off eventually. Good. Let's do exercise. Exercise is this where we see logarithms. So we calculate vortex function. We want to know poles of this stuff. We want to see where are the poles. So by construction, I remember what Cooper said. Cooper said, there will be instability, there will be logarithmical singularity when fermions have opposite momenta. Let me keep this. I use these words, and I put momenta k, so let me do it this way. I put momenta k and minus k. They obviously go into p minus p by momentum conservation. So what I need to do? I need to calculate fully dressed, anti-symmetrized vortex. Anti-symmetrization means that when I interchange two outgoing fermions, I put overall minus sign because these are fermions. And I do this, I put accurately spin indices, alpha, beta, gamma, delta. There are two combinations of spin indices because the spin is conserved along the direction line. So this is all standard curriculum of how to do calculations in the Fermi liquid theory. We'll do something more simple. We'll assume that interaction is just Hubbard. I don't have to do it, but it's lecture, so I don't need to write you long formulas on the blackboard. So let's see what we had. To first order, our vortex is just nothing interaction times some anti-symmetrized combination of spins, which tells you that this is a singlet channel. There is no triplet component. It's constant interaction. What else do you expect? It's only singlet. Very good. But of course, no pole. It's just simply U. OK, let's go to next order. Next order, we do all these calculations that it's a little bit boring. But there is one renormalization that come when I allow two fermions to keep going along the same direction. All these bubbles, when I didn't bother to put arrows, is just one arrow going in, another going up. This is what is called polarization bubble particle hole ones. This is where, in fact, logarithmical singularity comes from. And this is when you do calculations, you find that this guy, you will see formula in a second, general formula. If you do calculations at zero temperature, at momentum k and minus k, frequency omega and minus omega. So for two fermions here, total incoming frequency 0, total incoming momentum 0. You do this simple calculation at zero temperature, you get what? Question. What we get? Infinity. We really simply get infinity. Great. This is what's called Cooper logarithm. This is what Cooper found, that there is some infinity in the problem. Let's not look at the infinity. We ask the question, where are the poles? So we need to allow frequency to be non-zero. So let me now write the formula without infinities. I write exact result. It's trivial to do calculation, just convolution of two free fermion green functions. I calculate this polarization, particle-particle polarization, two fermions with the arrows in the same direction. At total momentum equal to 0, I still keep it 0, but I allow total frequency to be non-zero. This is my bosonic frequency, and I want to see where are the poles of this. So I need to keep frequency finite. And you see the expression for this polarization operator. Yes, it logarithmically singular. Omega goes in denominator. But there are two things to look at. First, that will eventually end up with Worth's Eliashberg theory. There is a scale, omega naught. What is the scale? I put it by hand. Otherwise, I would get infinity. Theory is formally ultraviolet divergent. I put it by hand by saying that let's suppose that interaction is a constant U at energies below some upper cutoff and 0 at energies above this upper cutoff. I have to do it, otherwise I will have infrared singularities in the problem. And this will be a sense of BCS. We put something by hand. So this scale is put by hand. And next one is this one. There is also, see, omega plus I delta. I shifted frequency a little bit into from real axis. But here is minus sign here. And this exact calculation. Log of -1 is equal to what? Actually, it's a bad question because you don't know whether it's plus I pi or minus I pi. But it's imaginary, right? Because it's imaginary, don't expect that you will have a pole at frequency very close to real axis. You will need to have solution. And solution means that real part should be 0, total, and imaginary part should be 0. OK, anyway, keep going. This is simple. What is done next? We have one diagram, which is logarithmically singular. Everything else is not. Let's forget about everything else. It's not completely rigorous, but let's forget about it. Then let's sum what's called ladder series, when I constantly add cross-sections with more and more particle hole insertions. And obviously, something like U1 plus something goes into U divided by 1 minus something. This is a full expression for vertex function within this approximation. Lambda is dimensionless coupling constant. And you see when U is positive, it's negative. When U is negative, it's positive. You look where you can expect a pole. Pole is where gamma goes to infinity. Denominator is 0. So obviously, when lambda is negative, positive U, you don't expect anything. It's 1 plus something big. So you definitely expect that something interesting may happen only if U is negative, means attraction. So remember, there are two questions. What causes attraction and what are the consequences? We are at the second question. We study consequences. Let's suppose that U is negative, that you have attraction. Then what? All we need to do is to take this guy and solve. But we know that for omega, this is a formula valid for omega very close to real axis. And because of minus sign here, we don't get a solution. So what we need to do, we need to go into frequency plane. We need to search for solution in the complex plane of frequency. I replace omega by complex z, a plus ib, and ask where is the solution? Does it exist? The answer is yes, it exists. Where? Well, the pole is in the lower half plane when lambda is negative. I made a mistake here. I erased an important line and left an unimportant one. So the next line which I erased will be in the upper half plane when U is negative. So when U is negative, the pole is in the upper half plane. And with erased statements, that was the main statements that I wanted to make. The pole is at z equal to IB when B is positive. So you have, and what is B? What's the solution for the pole? It's exponentially small in the coupling constant because of logarithm. Proportional to the unknown scale omega naught. But what we get? I did everything exact. I didn't tell you how I solved the equation, but you can solve the equation when you have 1 minus lambda times log of something equal to 0. You just solve it in a complex plane. What is the message here? The message here is that, interestingly enough, the system normal state surprisingly is unstable towards something. Unstable for arbitrary small interaction already. Of course, at larger interaction, it's more unstable. And it's unstable not because the theory has logarithm or something like this, but exactly because of this. You solve for where are the poles, and you find out the poles is in the upper half plane, which means I shift the system a little bit. I added something. Normally, everything with the added should decay. This is stability. Here, it goes up exponentially. It increases, increases, increases. And this means, this analysis means that system is unstable. So what Cooper said, yes, there's some logarithmical singularities, really leads to instability of the system. Very good. Near the pole, basically, you do it like this. Right. That's what I already said. Very good. Yeah.
I want to ask a very stupid, well, sorry. I want to ask a basic question. I don't know if it's stupid. But this choice of frequency or energy cutoff, can you not do that and just make a general argument for this to happen, or is this sort of divergence always going to be a problem?
You can make the general argument like this. You look at the equation, and there is some ultraviolet divergence of this equation. You can still say, yeah, I still believe that the pole should be in the upper half plane because of the structure of low energies. But you will not be able to say where are the poles. Because again, if we go back one step, the scale, which I put by hand, is the overall factor of here. If I don't put anything, the scale is formally infinite. So you really, yeah, you can wave hands, but nothing particular comes in. Yeah. No. Okay, good. So this I already said. This is interesting. Remember what we did? We said, let's put total momentum of two fermions to 0. I consider fermions with k minus k, right? What happens if I don't do this? It turns out that this was an important part of Cooper argument, because I can do all calculations, and I'm sure that any one of you can do these calculations. Is any way you calculate a particle-particle bubble of two free fermions. You can do it with non-zero total frequency. You can do it with non-zero total momentum. So you can do all these calculations, and here's what you find. You find that when total momentum is finite, only if this momentum is small, your pole is in the upper half plane. When momentum increases, there is a critical momentum when the pole goes into lower half plane. And lower half plane, poles in the lower half plane means everything is fine. Everything is, the system is stable. So if you create excitations with non-zero total momentum of a pair, and this momentum will exceed critical one, which by the way is the same order as what I wrote for B, up to V of Q is of the same order as B, then nothing will happen. You will get conventional behavior. And believe me, this was checked experimentally starting from helium-3. Yeah?
And where is the place for FFLO here on the diagram?
There is no place for FFLO at this stage. No. There is no place. I didn't add the magnetic field. So there is no FFLO here. No. Here, if momentum is finite, then you don't get it.
If you have a different sign of U with this graph?
No. That would be great, but no. Okay. No, it will not go this way. No. It will stay negative all the time. No. What you said would be absolutely great, but no. Okay. This brings me for a few slides to what was actually did by what is called BCS theory. Again, this theory exists in two versions. And I guess Nobel Prize was essentially given for version number 1. I may be wrong partly, but well, they did both parts. Let's start with first one, and then we talk about second one. So first part is genius of Bardeen to understand what this instability means. So we know there is instability. Pole is in the upper half plane means that if we allow perturbations, they will grow up exponentially. What it ends with should be some end point of this growth. And idea of Bardeen, which I will phrase a little bit in more modern language that was originally done in their paper, but it's all the same, is that if you start with the Hamiltonian, free fermions with some dispersions, and remember interaction, Hubbard U, this interaction between densities of fermions with spin up and spin down at the same side because it's on side U. Then idea was that let's check and verify that this instability leads to formation, spontaneous formation of a condensate of fermionic pairs. So if I take two fermions with momentum k and minus k and ask a question whether there is a condensate of this two-particle object, the answer is it's non-zero. And you assume this, and then you verify that this guy is non-zero. It's obviously spin singlet because we started with spin singlet. And in physical terms, it means statement of simple ways that yes, two fermions form bound state. Existence of B dagger average non-zero means that there is a bound state of fermions, and psi is nothing but wave function of this bound state. It has amplitude, it has phase. If time permits, we'll talk a little bit about fluctuations of the phase towards the very end of this talk, but at this moment, I'll just assume that phase is equal to 0, so I deal with real delta. I don't have to write down complex conjugated all the time. This is assumption. Again, it's like this. Again, I keep repeating the same. We know that the system is unstable. We try to find out what it ends with. Idea is that it ends it with this. And then you do self-consistent calculations, because once you have non-zero delta term, you can split quadratic form, four fermion term, and add extra quadratic terms. So you rediagonalize the quadratic form. You solve self-consistent equations. And at the end of the day, you get self-consistent equation of the parameter delta. This doesn't look as self-consistent equation, right? How the equation actually looks like. It looks like this. Delta is equal to delta lambda times this log. Delta is on both sides of equation. You express delta in terms of delta, which means one thing. Delta equal to 0 is always a solution. Of course, you started with something. If it's 0, then you end up with what you start with. But it turns out that it has another solution. Another solution with a finite delta. Lambda is the same parameters that we had before. Equation only has solution, of course, when u is negative and lambda is positive. And solution of this equation is the same scale as b. So obviously, yes, you had a scale which you knew from the normal state as a scale, essentially it's a scale at which excitation grow with time. E2 plus bt. And then it turns out that equilibrium delta is of the same order. Yes, please.
How do we set omega naught? Because how do we set omega naught? Because you said that omega naught is put by hand. And it seems that delta could be it's something that you can measure, like the math.
Very good, very good, very good. We're on the same wavelength. I tell you what the theory tells. And then we go to a situation, yes, delta is measured. How can we calculate delta? How can we calculate the scale? At this moment, it's just scale put by hand. Yeah, it's the right question. But this is where this is called Eliashberg theory of superconductivity. Well, OK, good. Again, one thing not often surprisingly mentioned in the textbooks, that the key effect, probably the key effect of all this analysis is that if you calculate now conductivity, for this you need to include some kind of scattering. In the normal state, that was a Drude formula. We know this, we started, it was first slide. In the state with non-zero delta, you calculate conductivity in the presence of impurities, and you get delta function. So in conductivity, there is a delta function and then some finite value after some minimal frequency. But delta function is very important. Delta function means that conductivity at zero frequency is infinite. Resistivity is 0. This is superconductivity. Or I didn't say anything about charged particles, so it's equivalent to the word superfluidity here. Good. Referring exactly to your question. Delta and TC are measurable in experiment. So you should be able to, or your desire to know what theory tells about them. BCS theory, this genius theory, to my opinion, is the nicest, most elegant, seriously, now it's most elegant theory of 20th century. I don't compare it with anything. Tells you that if you want to calculate TC, you don't know it because there is unknown scale. Yes, you can calculate prefactor here, but the scale is unknown, so calculation of prefactor is meaningless. You can go at 0 temperature and calculate the value of delta. You can also do this, and again, I showed you the formula. You get delta with prefactor, again unknown scale, and this exponent in both ways. However, this is the elegance of the theory. If you calculate the ratio of the two, delta over t, you get universal number. Prefactor, sorry, this overall scale omega naught cancels out, and you get universal number that, of course, has been verified number of times in experiments. Good. There's number of other universal numbers. For example, if you calculate specific heat jumps at Tc. And you calculate the ratio of the values immediately below Tc to the value immediately above Tc divided by the value of immediately above Tc, you get another universal number. And this number are both expressed theoretically in terms of zeta function, etc., etc. So these numbers, but numbers are really universal numbers. Very good. Detour for 10 seconds. Question, pretty much the same as you asked. Within this kind of considerations, not going beyond, can we calculate TC? On first answer, you say no, it's omega naught, unknown scale. In fact, there was an answer that yes, you can, in fact, even within this theory. But it's a trick. And trick is this. Suppose that my U or my omega naught is some very large scale. Very large means larger than Fermi energy. In fact, this story now resurfaced in the studies of superconductors with very small Fermi energy. So suppose that upper cutoff is larger than Fermi energy. Is the result Tc is omega naught times e to minus 1 over lambda? The answer is yes, it is. But story goes with the name of Lev Gurkov. We did it with his student Merik Barkhudarov in early 60s. Was very interesting. Gurkov said, well, it's true. I'm not going to do anything with BCS formula, I'm just going to rewrite it. And the idea is that U is not a measurable quantity. Because why is not measurable quantity? Because if you allow fermions to interact once, they will interact 2 times, 3 times, 4 times, etc. And quantum mechanics tells you that yes, this is the case. If you solve quantum mechanical equation for 2 interacting particles, you know what the result is. You measure the result of interaction in terms of for constant interaction in terms of scattering length, scattering function generally, scattering amplitude, sorry. Scattering length is a measurable quantity, a result of multiple interactions. Interaction itself claim it's not measurable, so let's try to rewrite the result in terms of measurable quantity, scattering length. Then we know quantum mechanically what's the ratio. Scattering length is proportional to interaction, but there's all corrections coming from the fact that if you have 2 particles in a vacuum, what means 2 particles in a vacuum? It's for momentum equal to 0, but there's no other particles. They scatter. And all these corrections are incorporated in the relation between U and scattering length. And then the idea is this. All this high energy physics, all this related to the cutoff, come from energies much larger than Fermi energy. So they're all parts of the renormalization of interaction in the scattering length. And actual superconductivity come from the logarithmical singularity at the Fermi surface. So it knows about the scales of Kf or Pf. So trick is this. You take this wonderful particle, I keep forgetting to put errors. Errors are all in the same direction. You take this 2-particle object. You have to calculate it as a product of 2 green functions with finite Fermi momentum. You subtract and add the same product with 0 Fermi momentum, just for 2 particles in a vacuum. This guy which you add goes into normalization of interaction into scattering lengths, but this part give you completely ultraviolet convergent integral. Because if you go to energies larger, or momentum much larger than PF, energy is much larger than Fermi energy, then this guy and this guy are the same. So you do calculations, and you find that this gives you a finite answer, and this just, again, rewrites U in terms of scattering length. There is a universal result. That TC is equal to universal number times Fermi energy times exponent, which contains scattering length rather than the interaction. You know what is this? This is BCS formula. Nothing was done, it's just rewriting. So this formula, and there is a confusion in the literature about this, even the confusion in the literature of 2023 about this. This is not new formula, this is BCS formula. But rewritten in terms of another quantity which is accurately claimed to be measurable quantity. So all high energy physics is here. This correction contains ultraviolet singularities. In other words, we don't care. System will take care of this. It's a measurable quantity. So anyway, this was the result known from more than, I guess, 60 years ago. Okay, this brings me to second part of BCS theory. So first part was this. If you have attraction, we know what it leads to. We know how to do calculations. We have some unknown parameter, omega naught. Second part, what causes the attraction? And for this, there is a version of BCS that more known in some circles is that it's electron-phonon interaction. It's not electron-electron interaction. You need foreign objects that mediate the interaction between electrons. And the story is told in various ways. You can find various hand-waving argument in the textbooks. Story goes is that one fermions comes in, create distortion of the lattice. Another fermions come to the same point, and the lattice reads the distortion. And through this distortion, two fermions are interacting with each other. These are words. For our purposes, this is what we need. There is effective interaction between fermions, not Hubbard U, but interaction mediated by phonon propagator. Very good. If you want to ask me the question how you can get superconductivity despite the presence of large repulsive Hubbard U, you can ask me a question during the question session. I'll be happy to answer. But let's now continue with what I said. I just replaced Hubbard U by this phonon propagator, because with Hubbard U I said Hubbard, and then I said attractive Hubbard. You can ask what the hell means attractive Hubbard. And this is a question I cannot answer. Story goes this way. Yes, if we consider a simple Einstein phonon, again, to making the story as simple as possible, then we know what this effective interaction is. It's a square of the coupling times propagator of this Einstein phonon. It goes like this because Einstein phonon has a pole at Debye frequency. And if you look at frequencies below this scale, it's important, at frequencies below this scale, then you find that this guy is out. You get minus sign here. So you get effective interaction, which is minus constant. So it's just like what we did before. We just got attraction. So this is the second part of BCS, that electron-phonon interaction at frequencies smaller than Debye frequency give you attraction. Take this note, because then I will say something crazy which will apparently, at a first glance, go opposite to what I just said. Good. Continue. Let's do what's called BCS for electron-phonon interaction. What they said? They said, let's keep interaction like this, and let's again introduce a scale by hand. But now we know what the scale means, Debye frequency. The question is it Debye frequency or Debye frequency divided by 2 or twice Debye frequency? This we don't know. We just introduce a scale of order of Debye frequency and set interaction is equal to 0 if fermionic frequencies are larger than the scale. I keep the scale as Debye frequency, but again, you understand it can be twice Debye frequency, half, we don't know. Once we do this, we have a theory with upper cutoff and with effective interaction, which is attractive constant. Everything I said to you before is valid. So you get the results. You immediately get the result. Same formulas that we had before. This is BCS theory for electron-phonon interaction. Same formulas, because its interaction is a constant at small frequencies. But we again don't know TC, and we don't know the gap function. They are all proportional to this scale, which in the theory is defined as the upper cutoff. Great. And now I can talk about, it was exactly half an hour, so after half an hour, I'm now going to the title of the talk. Great. So, Eliashberg theory of superconductivity. It exists in various forms. Eliashberg theory of superconductivity, Eliashberg theory for calculating of TC, Eliashberg computational procedure, etc., etc. So, some of this has nothing to do with the word Eliashberg. But we'll see. This is the only picture of Eliashberg I could find. Unfortunately, he died a few years ago at the age of 90. Yeah, it's a story about a person, about Soviet Union and all this evil of Soviet Union that kill people, maybe not physically, but morally. And he had a lot from what is called Soviet Union. Let's start with something simple. Let's go back to the same limit that I described to you before, weak coupling limit. Lambda much smaller than 1. Why it was much smaller than 1? Because we kept logarithm and neglected everything else. So then we definitely are working in a situation when all corrections are negligible, I neglect them, and this means that it's weak coupling limit. In this case, this is not Eliashberg theory done by Eliashberg. But in this case, you can ask a question. Can you do better than just putting upper cutoff in the theory? And the answer is yes, we can. And for this answer is don't do anything. In fact, the answer is simple. Don't do anything. You have interaction which is frequency dependent. Don't introduce upper cutoff. Solve everything as it is. And then you get effective interaction, which we don't approximate by step function. We keep it frequency dependence. And once we have it frequency dependence, we have interaction which depends on transferred fermionic frequency. Obviously, it means that the gap by itself, delta, becomes a function of frequency. So what you need to do, you need to solve integral equation for the gap. And graphically, it's like this. You can do what I did before. You can calculate vertex function, or, which is a little bit more easier, you calculate bare vertex with two fermions. Again, error should be up, out, out. You calculate bare B dagger, which called delta. You introduce bare one, and then calculate all corrections to this bare one by summing up this ladder diagrams, interaction, 2 interaction, 3 interaction. Every time in the cross section you get particle-particle polarization, and all these diagrams, all this ladder series, can be summed into one simple expression, which involves expression of full vertex in terms of itself, but at different frequency. So this is integral equation, which is nothing but what we did before. It's just rewriting of everything we did before in a different way. And what is nice, if I want to calculate where the system spontaneously develops non-zero delta, I don't need delta naught. I put it to 0. And I solve equation for delta of omega in terms of delta of omega prime. And if I put delta finite, of course, it affects what is in the cross section. So this is how you get self-consistent equation on delta. Looks like BCS, but delta is a function of frequency. So because of this, oh yeah, sorry, stop for a second. Now, one slide for disclosure. What I will do next, you will see number of formulas. Not much, but number of formulas. It's easier for me to give you presentations on what theorists like to call Matsubara axis. So I will tell you everything about superconductivity by going from real frequencies to imaginary frequencies. Why I'm doing this? You know all this. I'm doing this because on Matsubara axis, I can do calculation at 0 temperature, I can do calculation at finite temperature. On the real axis, I have to work hard to go from 0 temperature to finite temperature. So everything you will see next will be when frequencies are switched, omega is switched to I omega. It's a standard trick in theory. And if you want to do conductivity, you need to go back to real frequencies. If you want to calculate TC, delta, thermodynamics, then you don't need to do this. All thermodynamics can be done on Matsubara axis, just easier. And again, once I did this, you see interaction. It's negative. At this stage, I ask you, is it surprising? Not much. Okay, but now let me ask a question. Question is that previously what I told you. Interactions attractive if frequencies are smaller than the bifrequency. What happens if frequency is larger than the bifrequencies? It's repulsive, right? Look at this interaction. It's attractive at all frequencies, right? So there's something funny going on here. But it's exact. I just converted from one axis to the other. This will be subject of lecture. Good. We'll see that there is some physical differences between the two. Yeah, anyway, for all formulas will be on Matsubara axis. Green function on Matsubara axis is very simple. We don't need to put any I delta here, so everything is really simple. With this disclosure, this is the gap equation that comes out from self-consistent procedure. If you neglect frequency dependence here, if you neglect this guy, and just approximate interaction by a constant, it will be BCS gap equation. So again, I didn't go beyond BCS. All I said, don't introduce a cutoff. Let the system do whatever it wants. And here you get two things. First, this is integral equation that you need to solve, right? So this, theorists love this, right? You have integral equation, you can solve this integral equation, you get the result, you are happy with yourself, I will be. But you gain something. And gaining is this. Look at this guy. If frequency delta goes to infinity, interaction goes as 1 over omega squared. So now you have completely convergent integrals. You don't need to think, you don't need to introduce any cutoff. It's all there. So there is nothing to add to this theory. It's all convergent by itself. Because interaction goes to 0 when omega goes to infinity. That's what I said, right? There is a solution of this equation, analytical solution of this equation. At weak coupling, you can solve this equation analytically. Surprisingly, it was not done until early 90s. Second disclosure. We did it in 2014 with Yushan Wang, and we thought, gosh, are we the first? And it turns out that Igor Mazin did it in 1991, and in fact gave invited talk at APS only about this. But since then, it was not well known. Anyway, this can be done. It was done. This is the result. You get some number. You can express this number in terms of special functions, but it's not a big deal. Number times the bifrequency. This is the actual bifrequency. You don't put any cutoff in the theory. Good. The formula that is often cited for BCS is similar, differ by something like 2/3. This is 2/3 of this. But this is meaningless formula in this regard. I don't want to say anything bad. It's a great formula. But this scale in BCS theory, it's just upper cutoff. It's not the bifrequency. It's a scale of order of the bifrequencies that you put as a cutoff. Could be twice the bifrequency, 3 times, 5 times, or 1/2, whatever. So this is a real formula. It tells that if you have fermions, if you have Einstein phonon with the bifrequency omega d, this is your TC. Wonderful. And at this stage, you can ask a simple question. Great. Can we move on? No, we cannot. Because it turns out that this is not a correct result. By simple reason, but still not a correct result. And you may say, well, how can it be? I solved the equation at weak coupling. I solved it exactly. How can it be the result is not correct? Well, it turns out that at this stage, already at this stage, we need to look at the fermionic self-energy, which is small, obviously. But let's look into this. Let's calculate fermionic self-energy, again coming from interaction with the same Einstein phonon. You do standard calculations, and you find that, yes, you get self-energy, which is linear in omega at small frequency, so it just changes coefficient in front of omega, and changes it a little bit by the same coupling lambda. Great. What it means? You calculate particle-particle polarization, and it acquires, due to include self-energy here, it acquires coefficient 1 divided by 1 plus lambda. Again, you can say big deal. Lambda is small, small correction. Yeah, which means that my coupling lambda, which comes out as overall factor here, has to be replaced by lambda divided by 1 plus lambda. Again, trivial. However, in the formula for TC, we get exponent. We get e to minus 1 over lambda, right? Replace lambda by this quantity, you get extra factor 1 over e. This funny thing. At weak coupling, you look that you do everything right. It turns out that because of the exponent, you have to be more careful. My advisor, many years ago, he knew Landau, reasonably well, in fact. And he told me once a story about Landau, that he met Landau, it's old Soviet Union, so near the window where he get his monthly salary, and Landau was counting rubles one after the other. And according to my advisor, stories that I heard from my advisor, they called him Dow. Why you're doing this? You're a theorist. Look at the size of the pack. By order of magnitude, it's correct, right? And theorists always do calculations by order of magnitude. And the answer was the answer from great physicists. The money are always in the exponent, which means that you can do approximate calculations, but the exponent you have to calculate exactly. This is an example when you have to calculate exponent exactly, because minor correction to the exponent give you constant correction to the formula. So this is the correct result. Correcting everything. This is really correct result in terms of e to minus 1 over lambda. Good. Now, why I'm saying this, there are different forms of Eliashberg theory called Eliashberg. Eliashberg didn't do any of these calculations. It's only in his name, but really it's better called weak coupling story with electron-phonon interaction. This calculation has been extended and became big computational procedure for system with generally electron-phonon interaction, but not only electron-phonon one, all under the umbrella of weak coupling. So at weak coupling, story goes like this. Don't approximate your interaction by a constant. Take full frequency dependence. Take full momentum dependence. Take everything. Put it in a computer. Computer will solve integral equation. Solution of this integral equation will be TC. If you want to go below TC, you will get a gap function, which is a function of frequency. So you will get all this all weak coupling analysis. But of course, coefficients will differ, et cetera, et cetera. There is no completely universal about this coefficient. So it became big machinery, how to do these calculations and the number of results. That's why the theory became so popular that you had a simple equation, you put it in a computer gives you the result. Very good. Now, in the remaining 17 minutes of the talk, I will tell you about what Eliashberg actually did. And what he did goes under the name of strong coupling version of Eliashberg theory. Yes, please.
Under decoupling theory, do we have a universal structure of the delta of omega after
No, absolutely not. We get omega, we get delta of omega, which varies on the scale of order of debye frequency. How it varies, of course, if I solve for this particular problem of interaction with Einstein phonon, I get particular answer. If I change phonon propagator, I get a different answer. So there is nothing universal there. Okay, so here is the story. The story goes this way. Let's not think about small lambda. Let's look what happens when coupling becomes larger. And then, first of all, we need to look at higher order self-energy terms. Remember self-energy? This is a link. Self-energy was important even at weak coupling. So let's look at moderate to stronger coupling. Let's see what happens. Let's look at the next two diagrams. One is a normalization of internal propagator of a fermion. Another is a normalization of essentially the vortex between fermion and a boson. If I only focus on this, then I still can sum up all these diagrams, because all what they do, they transform internal bare fermionic line into exact. This would be part of more complex integral equation. If I look at this diagram, they do something different. They require you to calculate exact vertex function. Okay, let's look at these diagrams. First of all, the ones that convert bare fermionic propagator into full one. And it turns out you can easily do calculations. I skip details, of course, because otherwise we will be buried with details. These are expansion and powers of lambda. First order diagram already give you lambda. Second order will give you lambda squared, etc. So this is diagrams which become important when coupling becomes of order of 1, and when coupling is larger of 1, then you have to do this. But these diagrams, all they do, they convert bare green function to full one. You can still write down equation for the self-energy, but now equation will be sigma is equal to some integral of the full green function, but you know sigma is a part of the full green function, so it will be nonlinear equation in terms, nonlinear integral equation in terms of self-energy. Computer can solve it. What about the second part, vertex correction? On one hand, you can say, wow, vertex corrections are often associated with word identities, and this case is no exception. Number of particles is conserved. So if we look at vertex function, when incoming momentum is 0, incoming frequency is finite, by word identity, this vertex correction will be the same at frequency dependence of self-energy. It will be lambda. Higher order terms will be higher powers of lambda. So it's apparently of the same order. But the story goes that what we need, going back to interaction with Einstein-Phonon, typical momentum transfers, what we consider, are of order of Fermi momentum. There is no momentum dependence on of the bosonic propagator. So all integrate over all transferred momenta close to the Fermi surface, say from kf to minus kf. It's the maximum I can do. So momenta are all between 0 and 2 kf, which means the typical momenta of order of kf, or pf here. I could call pf. So typical frequencies are of order of Fermi energy. Sorry, typical VFQ are of order of Fermi energy. Typical frequencies that I need to put in are of order of Debye frequency, which is much smaller than Fermi energy. We played this game. We said that we don't want anything at higher energies. With interaction already give you convergence at energies smaller than Fermi energy. Then we're in the opposite regime. We're in the regime when essentially Q is large, omega is small. And in this case, it turns out that vertex function is determined by a different parameter. And this parameter is lambda times small ratio of Debye frequency over Fermi energy, nothing but small ratio of typical frequency and typical VFQ. And this is another parameter, which is much smaller than the original lambda. And as a result, we have two different scales. And physics here is this. You have fermions with whose effective velocity, omega d divided by k, is much smaller than Fermi velocity. And if you read diagram, it's always good to read diagram in physical language. And if you read vertex correction diagram, it tells you that fermions are forced to vibrate on bosonic frequencies. Because their bosonic frequencies are far away from their own resonance, they are far away from resonance. So there is no resonance scattering of fermions in this situation. And this goes to the idea of fast electrons and slow bosons. So any vortex correction forces fast electrons to vibrate on slow bosonic modes, and as a result, the process is not resonance one, it is reduced by the ratio of two energies. Very good. There is one more thing which we do quickly. What about effect of fermions on bosons? Landau damping. It's there. So you can also look at what this guy gives you when you look at correction to bosonic propagator, again at frequency omega momentum q, because because bosons can scatter into particle Hall pairs. We know what it gives you. It gives you Landau damping, them proportional to omega, formally inversely proportional to q, but q is large, so it's basically 1 over Fermi energy here. You can do calculations, and you find out that this is another process that is irrelevant to you. Because if you include this guy, assume that typical Q is of the order of Fermi momentum, then here is the form of the propagator that you get. This was the original one, omega d square and omega square. There were two terms that we started with. Landau damping gave you a term which is mixed between this linear and omega. It's proportional, I put it like proportional to omega d, and then it turns out that it has the same factor lambda e, second parameter. You look at this formula and ask lambda e, suppose that lambda e is small. Is this term relevant? The answer is no. You can easily calculate that in one limit is much smaller than this term, in the other limit is much smaller than this term. So it's always irrelevant. Means that as long as this parameter lambda e is small, vortex corrections are irrelevant, and correction to bosonic propagator are irrelevant. Therefore, one can ask a question. Can you do calculations when on one hand, coupling is already large, on the other hand, coupling times this ratio of two small parameters, Debye frequency and Fermi energy is small. And this is what is called Eliashberg theory. This is what Eliashberg did. Calculations in this limit, when on one hand coupling is larger than Debye frequency, remember the ratio of the two is lambda, but it's smaller than much larger parameter, Debye frequency times Fermi energy, the ratio of this guy to this guy is lambda e. In this case, remember, vortex corrections are out, but we need to put full green functions into expression for the self-energy. The result is, this is what I said. You can write it diagrammatically. Self-energy is still one loop diagram with the full green function. When you calculate, I called this previously delta. For the full green function, people call it phi. It's just renaming it, because delta is called different. You will see it. It's nothing. It's just different letter for the same quantity. So you write down self-consistent equation on the, again, gap function called phi. And you again have to put full green functions. If you want to solve for TC, this is all you have to do. If you want to solve below TC, of course, you need to include normal and anomalous green functions and do all this wonderful machinery, or matrix number stuff. Here's the equations. These are called Eliashberg equations, real Eliashberg equations. You do all integration over momentum because your bosonic propagator is momentum independent. You get integral equation, nonlinear equation for the self-energy, which on one hand is proportional to self-energy, on the other hand contains self-energy in denominator. You get nonlinear integral equation on phi, which is easier here, is proportional to phi, just like delta was proportional to delta. It contains self-energy in denominator, and of course it contains phi itself in denominator. But most important, it contains self-energy. So this is really set of two coupled integral equations. And what is this? This is nothing but bosonic propagator, right? Good. So this is canonical equations. Again, computer will solve this for you. There is a trick one can do. Yeah, first of all, yeah. You look at this equation. And with just nothing but careful looking at this equation tells you that there is a one overall scale given by omega d. There is a scale of coupling given by the ratio of g squared over omega d squared. And if you want to ask what is TC, remember all frequencies which I have here, it looks like omega, and I sum over omega prime. These are Matsubara frequencies, pi t to n plus 1. So in fact, I can pull out t and sum over numbers. And if you do this, you find out immediately that TC is Debye frequency times some function of the coupling constant. We know we coupling result. 0.25 Debye frequency e to minus 1 over coupling, so it's fine. But this works for any value of the coupling. Again, as long as we are in the limits that I described. Good. There is one funny trick we can do with these equations. You can introduce a function which actually called gap function. This function phi is more called like anomalous self-energy or vertex or anomalous vertex function. You basically take phi, multiply by omega, and divide by omega plus sigma. If sigma is 0, you go back, phi is the same as delta. That's why it's called gap function. You can also introduce what's called quasi-particle normalization factor by writing omega plus sigma divided by omega. You can say change of notations, nothing else. But you look at these two terms that were present in the equation on the previous slide. Phi divided by square root and omega plus sigma divided by square root. And you see with this change of notations, they look exactly like in BCS theory. Delta divided by square root of omega square plus delta square, etc. As if interaction was not there. You can rewrite equations like this. And you find out that equation for delta is still integral equation expressed in terms of delta only. The difference between weak coupling and this equation is actually this term. This term comes from self-energy. If I pull out this term on the right-hand side, you'll find that there's nothing but self-energy result. So equation formally looks similar, but with this term present. Good. And it's delta in terms of delta. So ask computer to solve it. It's just one integral equation, not two coupled integral equation, just one. And then what is z? Z is expressed in terms of delta only. There is no z here. So how it means? Solve for delta, solve this integral equation, find the result. Once you find the result, substitute it here, calculate z. This is not an integral equation. This computer can do in seconds. So it turns out that Eliashberg equation is a single equation for delta. Very good. I am almost running out of time, so I will say this in one phrase. Good. This can be done diagrammatically, and I showed you how to do it diagrammatically. Or this can be done by using Latinger word functional, writing Latinger word functional, neglecting vortex correction and Latinger word functional, and then all this machinery is here. All you have to do is to write down stationary condition, that variation of Latinger word functional over self-energy, over normal self-energy, anomalous self-energy, they're all zero. You get set of two equations, you integrate over momentum, you get exactly the same as it was before. So you can do it either way. You get the same result. Very good. Yeah, let me say one phrase, and maybe I will stop here because I have time at the beginning of the next lecture to, actually next lecture will be continuation of this. I promised to tell you that there are three things associated with the word of Eliashberg. This is weak coupling story when you put essentially BCS-like gap equation into computer. If you know bosonic propagator, computer will tell you what is TC, what is delta. This is normally called Eliashberg equations. As I said, it has nothing to do with the word Eliashberg. It's just weak coupling equations when you don't approximate, don't do any approximation. You don't introduce hard cutoff, you allow the system to introduce cutoff by itself. This is first computational procedure. There is Eliashberg equation which were obtained by assuming that there is a small parameter in the problem lambda e, while parameter lambda can be arbitrary, and you write down set of two equations, which turns out to be one nonlinear integral equation, which you solve. This is canonical Eliashberg theory. And there is a third version of Eliashberg theory, which also sometimes goes in the name of flex fluctuation exchange approximation, and there are several other words introduced like this. It's like this. Neglect vertex correction, close your eyes, forget that you have small parameter or large parameter, whatever, include everything else. What it means, include everything else. Don't neglect Landau damping, don't neglect generally correction to bosonic propagator. Write down three equations. Equation for self-energy, equation for anomalous self-energy or the pairing vertex, and equation for the polarization operator. We said don't do this, but let's do this. All equations, since I neglected vertex corrections, all equations can be written in terms of full green functions. Moreover, once this guy is included, it gives you momentum dependence of the polarization operator. This immediately produces you momentum dependence of the self-energy. This immediately produces you momentum dependence of anomalous self-energy. You have a set of three coupled equations. You can actually convert it into 2 and 1, but it's still a set of coupled integral equation. Computer can do it. This is called Eliashberg computational procedure. When you put everything in, only thing you do, you neglect vertex corrections, and then ask what will be the question. And again, you cannot solve this analytically, but you can solve this numerically. It turns out, however, that if you play the game with small parameter lambda e, it turns out that you neglect some terms of order of lambda e, and you include some terms of the same order. In particular, this guy will be small in lambda e, and any momentum dependence of the self-energy will go in powers of the same parameter lambda e, while frequency dependence will go as powers of this different parameter lambda. And if this guy is small, you can neglect this. So basically, this computational procedure, I don't want to say anything bad. It's real computational procedures that give results. And it can well be that you can do this, and it turns out by some numerical reasons vertex corrections are small, so you basically, yes, you neglect terms of the same order, but they may be small. But this is from theory, from point of view of theoretical stuff, you include some corrections of order lambda e and neglect others. I told you the last thing, very last thing, I'm done in a second. TC. I told you that it's dBi frequency times function of lambda. I told you that with coupling we get omega d e to minus 1 over lambda. What we get as strong coupling? It turns out that a strong coupling we get TC, that dBi frequency times square root of lambda. It was done by Alice and Dyens in 1975, phenomenologically in fact, without actually solving equations, saying that it should be like this. They were right. It turns out, but there is interesting stuff here. What's lambda? G squared over omega d squared. Substitute it here. You'll find that TC is of order of G, right? And what it means? I can take the bifrequency and make it very small, and my TC will be much larger than the bifrequency. This formula already tells you this. When lambda is large, TC is larger than the bifrequency. Let me finish this lecture with a statement. How can it be? We started by saying that fermions are that there is attraction by phonons. If frequency is smaller than the bifrequency, there is a repulsion if frequency is larger than the bifrequency. And I get temperature which is much larger than the bifrequency. How can it be? I stop here. Second lecture will be later today. Go ahead.
In VCS, the delta is related to the spectral gap. So when delta is no function of omega, so how would we interpret the spectral gap? Would it be like the delta at omega equals 0 or something like that?
To a certain extent, yes. You need, when you say spectral gap, here's what you need to do. You need to calculate spectral function. Okay. And it turns out that because delta at 0 frequency approaches a finite value, then there is a gap. But what is the value of this gap? It's not exactly delta at 0 frequency. It's some number of the same order, but you need to do calculations. Same with conductivity. Where conductivity, there is a delta function, and there is a non-zero part. Where it starts, you need to do calculations. But because delta at 0 frequency approaches finite value, you do have real gap in the spectrum.
Is there a possibility that delta at 0 frequency is 0, but on other frequencies non-zero?
It's called odd frequency superconductivity. Okay. Every time when you have interaction, which is a function of transverse frequency, I didn't tell you about it, but good that you asked, have two types of solutions. One is even frequency, then it's finite at 0 frequency. One is odd in frequency. Both are allowed. It turns out that for this case, odd frequency solution is not logarithmical and always loses compared to even frequency solution. There are people like Sasha Balatsky who are trying to search for exotic situations when odd frequency superconductivity develops. You don't need strong coupling for this. You need special conditions. But yes, the answer is it's possible. It's another type of solution, exactly as you said.